Welcome to lecture 4, and the topic of this lecture is diode models. What is model? A model is a representation of a component or circuit that demonstrates one or more of characteristics of that component or circuit. For example, DC model of capacitor and AC model of capacitor. In the case of DC model of capacitor, may represent the component as a open circuit since a capacitor block DC. At the same time, the AC model of the capacitor may represent the component as a variable reactance, and the reactance of the capacitor is inversely with the frequency. Types of diode model. So there are three types of diode model. The first diode model that we cover is ideal diode model. This model represents the component as a simple switch that either closed or open. So the ideal diode model is typically used in initial stage of circuit analysis and troubleshooting. And the second type is the practical diode model. The practical diode model is a bit more complex than the ideal model. The practical diode model include the diode characteristics that are considering when performing the mathematical analysis of a diode circuit, determine whether a given diode can be used in a given circuit. And the third type is the complete diode model. The complete diode model is the most accurate of the diode model. It's include two diode characteristics that are generally considered only for circuit development. The ideal diode model. The ideal model of a diode is the least accurate approximation and can be represented by a simple switch. When the diode is forward biased, it ideally acts like a closed switch, and open switch when the diode is reverse biased. In this figure, you can see when the diode is forward biased, the diode is changed with a closed switch, and when the diode is reverse biased, there is no current flow through the circuit and the diode changed with the open switch. So based on the characteristics of a switch, we can make the following statement about the ideal diode. When reverse biased, so in B figure, when reverse biased, the diode has infinite resistance. The diode does not pass the current. So when the switch is open, no current flow through the circuit. The diode drops the applied voltage across its terminal. So in the case of reverse bias, the voltage across the diode is equal to the terminal voltages. So in the case of forward bias, we can say the diode has no resistance. So the diode does not limit the circuit current. And the third is the diode has no voltage drop across its terminals. So this is a graph of ideal diode model. In this graph, this is the axis of VF. VF is forward bias voltage, IF forward current, VR reverse voltage, and IR in the reverse leakage current. So when the diode is forward biased, no voltage drop across the diode. So you can see, regardless the value of IF, the voltage drop of diode is 0, and at the 0 voltage the current saturated. And in the reverse bias, you can see the terminal voltage and in the reverse bias graph, you can see the voltage across the diode is equal to the terminal voltage because the switch has open. The practical diode model. The practical model includes the barrier potential. When the diode is forward biased, it is equivalent to a closed switch in series with a small equivalent voltage source. Vf is equal to 0.7 equal to the barrier potential 0.7 with the positive side towards the anode. In this figure, you can see we replace the diode with a closed switch with a series of a VF battery source, and the value of VF is equal to 0.7 for the case of silicon and 0.3 for the case of germanium. So this is a forward bias condition, and in the reverse bias condition, the reverse bias condition of the practical diode model is the same of the ideal diode model, and the difference between the both graphs only the value of 0.7 volt, and this value is actually the knee voltages. So when you add the loop equation in this forward bias, the loop equation is V bias. Actually the V bias is equal to gain voltages, and the gain voltage equal to IF, the current flow through the circuit, multiplied by R limit, IF multiplied by R limit, plus the voltage drop of the diode, and this is a VF. VF is equal to 0.7 volt. The complete diode model. The complete model of the diode is the most accurate approximation and includes the barrier potential, the small forward dynamic resistance, and the large internal reverse resistance. And the reverse resistance is taken into the account because it provides a path for the reverse current, which is included in this diode model. In this figure, you can see a dynamic resistance added with a series of VB, and VB is equal to 0.7 volt. Actually VB is a VF, and in the case of reverse bias, this is a large internal reverse resistance. So you can see a slope due to the low forward dynamic resistance, and in case of reverse bias, small reverse current due to the high reverse resistance. Because the value of the reverse resistance is very high, some small reverse current flow through the circuit in the reverse biasing.